In Chapter 7.4, we're looking at qualitative variables and whether somebody has the characteristic or does not have the characteristic. And so in this particular case, we can construct a sampling distribution for a sample proportion. And we will use the central limit theorem to compute probabilities for the sample proportion. Objective 1. Construct the sampling distribution for a sample proportion. In a population, the proportion who have certain characteristic is called the population proportion. The population proportion is denoted by P. In a simple random sample of n individuals, let x be the number in the sample who have the characteristic. The sample proportion is p hat is equal to x over n. So for example, if we're taking a sample from our class data to see how many people had blue eyes, then x is equal to the number of people that have blue eyes, and n is equal to the class size. Another example is a computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot serve everyone in the city, so she draws a sample of 100 people and survey them. It turns out that 35 out of the 100 people in the sample own a laptop. So in this particular case, the sample proportion, p hat, is equal to 35 divided by 100. The proportion of people in the entire city who own the laptop is called the population proportion, P. In several samples are drawn from a population, they are likely to have different values for p hat. Because the value of p hat varies each time a sample is drawn, p hat is known as a random variable. And it has a probability distribution. So in the last example, each sample had 100 folks. So n equaled 100. And so each time we sampled the population, we were sampling 100 people, and p hat could vary from sample to sample. So the probability distribution of all the p hats in the sampling is called the sample distribution of p hat. Consider tossing a coin 5 times. This produces a sample of size n equals 5, where each item in the sample is either a head or a tail. The proportion of times the coin lands on heads is the same proportion of p hat. The probability that it lands on each time is 0.5. Therefore, the population proportion of heads is p is equal to 0.5. All 32 possible samples are presented below. So the table displays all possible samples of size 5 and their sample proportion p hat. So we'll call this p hat. Actually, maybe I should write it a little better. P hat. This is p hat and p hat. So in each one of these cases, the number of times the heads appears in 5, well in this case it's 0 for tails, tails, tails. The number of times heads appears in 5 chances here is 0.2. The number of times heads shows up in this one is also 0.2 since heads is only shown up once. When heads shows up twice in a sample, it'll be 0.4. When heads shows up 3 times, it'll be 0.6. When heads shows up 4 times, it'll be 0.8. And when heads shows up for all the times, it'll be 1.0. The mean of all the values of p hat is Guess what? 0.5. And the standard deviation of all values of p hat is called sigma p hat, which is the standard error, which is 0.2236. Next, we will compare these values to the population proportion 0.5 and the sample size 5. In the previous table, the mean of the sampling distribution, mu p hat, is equal to 0.5, which is the same as the population proportion, p is equal to 0.5. This relationship always holds. The mean of the sampling distribution of p hat is denoted by mu p hat and is equal to the population proportion, mu p hat is equal to p. The standard deviation of the sampling distribution, sigma p hat, is 0.2236. It's not immediately obvious how this relates to the population proportion p or its standard deviation. The sample size n and the sample size n. Note, however, that sigma p hat, which is now called the standard error, is 0.2236. And it is essentially the square root of 0.5 times 1 minus 0.5 divided by 5, which in this case, if we look at the symbology, it's nothing more than the square root of p times 1 minus p divided by n. This is called the standard deviation of the sampling distribution of p hat and is denoted as follows. We also call it the standard error of p hat. So in our picture, we have the population with a random variable p, right? So these are the values that p can take on for our coin, 5 coin toss. And then if we start looking at the number of tosses included in that each time we conducted the experiment, this now becomes p hat. So the probability histogram for the sampling distribution of p hat for the proportion of heads in 5 tosses of a fair coin is presented. We can see that the distribution is reasonably well approximated by a normal curve. The experiment is conducted again, but with 50 tosses of a fair coin. As we increase the number of tosses, the sampling distribution of p hat is more closely approximated by a normal curve. When p equals 0.5, the sampling distribution of p hat is somewhat close to normal, even for a small sample size like n equals 5. When p is close to 0 or to 1, a larger sample size is needed before distributing p hat is close to normal. A common rule of thumb is that the distribution may be approximated with a normal curve whenever np or n times 1 minus p are both at least 10. So here's an example of the sampling distribution. The soft drink cups at a certain fast food restaurant have tickets attached to them. The customer peels off the tickets to see whether they win a prize. The proportion of tickets that are winners is equal to 0.25. A total of 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let p hat be the proportion that win a prize. Find the mean and standard deviation of p hat. The population proportion, p equals 0.25. The sample size is n is equal to 70. So the mean of p hat is 0.25. And the standard deviation of p hat is, when we do the calculation, 0.0518. So again, the central limit theorem for proportions will hold. Let p hat be the sample proportions for a sample size n from a population with a population proportion p. If np is greater than 10 and n1 minus p is greater than 10, then the distribution of p hat is approximately normal with a mean mu p hat is equal to p and a standard deviation or standard error is equal to the square root of p times 1 minus p divided by n. We want to make a note here that if np is not greater than 9, or n times n minus p is not greater than n, then we use the binomial to calculate probabilities. So in other words, if it's less than 10, right? If np is less than 10 or n minus p is less than 10, we use the binomial distribution to calculate probabilities. So here are some examples where the central limit theorem may or may not apply. A sample size of 20 is drawn from a population with a population proportion equal to 0.7. Is it appropriate to use the normal distribution to find the probabilities for p hat? The answer is no, because n times p is okay, it's equal to 14, but n times 1 minus p is equal to 6, and that's below 10. So in that particular case, we cannot use the normal approximation. A sample size of 55 is drawn from a population with the population proportion p is equal to 0.8. Is it appropriate to use the normal distribution to find the probabilities for p hat? The answer in this case is yes, because np is 44 and n times 1 minus p is 11. Both are greater than 10, so the distribution is approximately normal. Objective 2. Use the central limit theorem to compute probabilities for sample proportions. According to the Harris poll taken in September 2013, chocolate is the favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 30%? So, we draw our probability distribution, and in fact, this is our sampling distribution, right? Which is p hat, right? Sampling distribution. And from our sampling distribution, we can write a probability statement. The probability that p hat, we ask the question, is greater than 0.30, right? So now we first check our assumptions. np, 100 times 0.27, well, 27 is greater than 10. And n times 1 minus p is 100 times, well, 70.73, which is 73, and 73 is definitely greater than 10. We may use the normal curve. So now we know what the mean value is. In this case, p hat, mu p hat, is 0.27, and the standard error in this particular case is 0.4439. We can use the normal CDF function here, which the lower bound is 0.3, the upper bound is 1e99, mu in this case is 0.27, and the standard error is 0.044396. The bigger the number, the more decimal place we go out for the standard error, the more accurate our estimate is. So in this particular case, the probability that the proportion of Americans who prefer chocolate greater than 30 is about 25%. We'll now do the same calculations, but now we're going to do them by hand. So here we have the same problem. We have our probability statement like we did last time, and now we're going to take this and do it by hand. And the first thing you'll notice, I've transferred, since our z-table cannot calculate probabilities above the value for p hat, we now have to do the complement. 1 minus the probability of p hat, right, less than 30. And then again, we transfer the p hat to a z variable so we can read the table. Don't forget how we do the z. The z is going to be, in this case, our z, how we're going to transfer it, is p hat minus p divided by sigma p hat. So that's what we did here. And we get a z value, z less than 0.6753. Obviously our table doesn't go out to 4 digits, so we round up to 0.68, and now we go look at the table, and from the table we see that it is 0.7517, but guess what? We subtract it from 1 and we get an answer of 0.2483. So we're off a little bit, primarily rounding error, and certainly the table is not perfect as well, and we have to do some rounding. So that's the answer if we did it by hand. So here's another example. In the 2012 U.S. presidential election, 51% of the voters voted for Barack Obama. If a sample of 75 voters were polled, would it be unusual if less than 40% of them had voted for Barack Obama? First, we check the assumptions, NP. We get 38.25, which is greater than 10, and then we do the other, n times 1 minus p, which we get 36.75, which is greater than 10. And so we can use the normal curve. So now we have the curve. We can see how this curve works for p hat, the sampling distribution. So now we're computing the probability that p hat is less than 0.40. That's what we're looking for. So we know what the mean value is. It's 0.57, and the standard error is 0.57723. Again, you don't want to round this if you can possibly avoid it. And then we plug it into the normal CDF, just like we did the last one. And you can see that, here's the lower bound, here's the upper bound, here is mu, and here's the standard error. And so we get that the probability of the occurrence of seeing less than 40% of any small group of folks, or 75% of the voters polled, be less than 40% is about 2.8% probability. And so it would be unusual for the sample proportion to be less than 40 in this particular case. So in this section, You should know the notation for the sample and population proportions. How to construct the sampling distribution for a sample proportion. How to find the mean and standard deviation or standard error of the sampling distribution of p hat, and how to use the central limit theorem for proportions to compute probabilities for the sample proportion. So this concludes our two sections on the sampling distribution, and I want you to realize that there are some things you need to know about. We've talked about the random variable x, the random variable z, and in this section the random variable x bar. We've also looked at p and the random variable p hat. So these two variables have sampling distributions. Which we've looked at so far. These two variables, one is a qualitative and one is a quantitative variable, have population distributions. The difference between the population distribution and the sampling distribution is like the difference between an individual and a group. And so that's the way I would like you to look at these two types of distributions. That concludes this particular chapter.